So we're going to take the next step in looking at electrochemistry. You already learned about activity series. Now we're going to take a look at the official activity series that scientists use, and that is called a standard reduction potential series. So this organizer is page 1207. That's the only page we're going to take a look at today. The back side is going to be another video. So if you remember, because redox reactions involve the movement of electrons, we can generate an electron potential. Each of the half reactions that exist have the potential to generate a certain amount of energy. And so scientists have created a reduction potential table that shows you, here it is, this is Appendix 11 for you guys. It shows you the different values of the electron potential of the movement of the electrons in that reaction. So for example, fluorine gaining 2 electrons to become fluoride has a huge reduction potential. That's a lot of potential voltage available if used in the right way. And then you look at things like, all the way at the bottom here, you've got potassium and you've got lithium. They have negative voltages. So we'll talk about what that means. But basically, this is a standard reduction potential series. And the numbers that you see are the voltage associated with that half reaction. So to figure out how much voltage you get from a redox reaction, we have to combine the two half reactions and then calculate what the value is. So going back to the organizer, if you just start throwing reduction potential, if you just start throwing half reactions together, there's no kind of standard. So what scientists have done is they've set the standard half cell as hydrogen gaining electrons to become hydrogen atoms. They've given that voltage 0. So then what they've done is they've set up redox reactions with hydrogen and every other element and chemical that undergoes oxidation and reduction and measured the voltage that you get with that. In that way, so for example, setting up hydrogen with fluorine gives you a voltage that is 2.87. So that value, because they've said hydrogen is automatically 0, for that value, we attribute that strictly to fluorine. And so sometimes you get a positive voltage when you put that chemical against hydrogen. Sometimes you get a negative voltage when you put that chemical against hydrogen. And so it's all relative to how it compares against hydrogen. So when you're looking at figuring out the voltage of a cell, there's a few things you need to remember. Notice on the reduction potential sheet, they are all reduction potentials. They're all half reactions that show reduction, the gain of electrons. So if something is undergoing oxidation, you actually have to not just write the reaction inverse, you have to change the sign of the voltage. So if you flip the half reaction to make it oxidation, you have to change the sign of the voltage. So if it was positive, it becomes negative. It was negative, it becomes positive. The one thing you don't do, however, and this is different than what we did in thermo, you don't multiply the voltage by the coefficient that you have to multiply the equation by. So if I have to, in order to get the electrons to balance out, I have to multiply a half reaction by 3. I don't multiply the voltage by 3. So that's something really important to remember. You don't multiply the voltage. You just keep the voltage as it is. You flip oxidation value reactions as well as signs for the voltage. So then you sometimes wind up with positive voltage and you sometimes wind up with negative voltage. If you wind up with a positive voltage for the entire electrochemical cell, that is a cell that could act like a battery. It generates its own energy. It is called a galvanic cell. So if you get a positive voltage, that means it's a galvanic cell. That means it will be spontaneous. It will run on its own. If you get a negative voltage, that's called an electrolytic cell. Those cells require energy. So you have to hook up those cells to a battery or to a wall unit or something to get that reaction to work. So those reactions are not spontaneous. You have to input energy in order to get that reaction to work. So that's how you want to interpret the positives and the negatives. So now what I want to do is just do some practice. So this is going to combine a lot of the ideas that we've already been doing. Let's move this sheet so you're not seeing it underneath the page. All right, so start off with something simple. We've got Au3 plus going to Au and Cu going to Cu2 plus. So you know these guys have a zero charge, right? So Au is going from plus 3 to 0. Cu is going from 0 to plus 2. So copper's losing electrons. Gold is gaining electrons. So the copper is undergoing oxidation, and the gold is undergoing reduction. If we were to balance this, we've got 3 electrons moving here. We only have 2 electrons moving here, so hopefully you've done enough of these that we need 6 electrons moving, and that's the way to do it. So I could go through all the details, but I'm hoping you're good enough that you can see that's what has to happen. These are pretty simple reactions to balance. All right, so I'm going from Au3 plus to Au. That's reduction. So if I look on this sheet, I can pull that value straight off the sheet. And here it is. Au3 plus to Au is 1.50 volts. So the E of reduction for Au is 1.50 volts. That's a positive 1.50 volts. If I find the copper, so I'm going copper and copper 2 plus, you see a few different coppers. Make sure you pick the right one. Here's copper 2 plus to just copper plus 1. Here's the one that I want. Okay, so be careful. Make sure you're looking at the right equation. That for reduction, it is positive 0.34. So Cu reduction is positive 0.34. But one of these has to undergo oxidation. And like I said, we can see that the copper is what's undergoing oxidation. So what I need to do is I need to change this to the oxidation voltage, which is 0.34 negative. Okay, so this is kind of irrelevant now. So if I add these two up, what voltage do I get? 1.16 positive. So the voltage for the cell, the standard voltage for the cell, and usually we put a little naught there for standard. The standard voltage for the cell is 1.16 volts. Okay, so the unit for that is volts. So that's how I can figure that all out. All right, how about the iron to the iron, iron 2 plus with silver? So what's going on? We go silver 0 to silver plus, so silver's undergoing oxidation. Iron plus 2 is going to iron, so that's gaining electrons, that's undergoing reduction. So now we can pull those values out. Again, we're just pulling directly off the sheet first. So I've got, what was it, silver? I forgot. Silver going to, so here's silver 2 plus to silver plus. We want silver plus 1, no, that's, yeah, there it is, 0.8, okay? So for silver, it's 0.18. No, 0.80. What am I doing? 0.80. Sorry about that. For the iron, going to iron 2 plus, again, pulling right off the sheet, Fe to Fe2 plus, here it is over here, negative 0.44. Now, one of these has to be flipped. So we're going to flip the oxidation one because that's what we figured out in the equation. So this is going to become a negative 0.80. So negative 0.80 plus a negative 0.44 is not a positive. It's a negative 1.24. So the voltage of the cell is negative 1.24. Okay, so this one up here was positive. That's going to be spontaneous. That can act like a battery. But this one with the negative voltage, that is not spontaneous. So I would have to supply energy to get this reaction to go. And hopefully you remember when we did all those different experiments, silver always wound up being the metal. We hardly ever had silver stay an ion. Only if we would use something like fancy like gold would that happen. All right, so that's the metals. Let's take a look at something where we don't have metals, we have nonmetals. We didn't really do this before, but same thing's going to hold true, right? We're going from I2 to I minus. Now here it's going to be a little different. To balance it out, I actually need 2 of each of those there, right? I2 to I minus, I'm still gaining electrons there, so that's reduction. Fluorine is going from F minus to 0, so that's undergoing oxidation, that's losing electrons. So if you remember, the very largest reduction potential was fluorine, but it was fluorine gaining electrons, not losing electrons. So here is a positive 2.87, but here it's actually going to be a negative 0.287. So we've got the oxidation of fluorine is a negative 2.87. And then for iodine, it is undergoing reduction, and iodine is, there we go, iodine is a positive 0.54. So I add these two together, and overall, what's my sign? The cell voltage is negative. So is this reaction going to take place spontaneously? Nope, I'm going to have to force this reaction to take place. I'm going to have to put energy in order to get that reaction to work. And what is the voltage? 2.33 negative. And that's volts. They're all volts. All right, so 2 more here. Why don't you pause, try and do those on your own, and then we'll take a look at the answers. Okay, so hopefully you took a moment and started to do those. I've got chlorine gaining electrons. So chlorine is undergoing oxidation. Reduction. Hello. Chlorine's gaining electrons. It's undergoing reduction. So the voltage for chlorine, hopefully you found, was 1.36. For sodium, going to sodium 2+, that's undergoing reduction. Oh my gosh. That's undergoing oxidation. If I find that on the sheet, sodium ion going to sodium reduction is a negative 2.7, which means oxidation is a positive 2.7. That's the favored system for sodium. Positive 2.7. Look at that voltage. That's huge. 4.07 positive. So that's why sodium chloride, Na plus Cl minus sodium chloride, is such a common substance. Much more common than sodium metal is because of the voltage. Last one, I stuck with all ions just to make sure you were staying on your toes. So chromium to chromium plus, chromium 3 plus to chromium 2 plus, that's gaining an electron, so that's undergoing reduction. Fe to Fe3 plus, Fe2 plus to Fe3 plus is undergoing oxidation. So we've got the 2 half reactions. Lost it. Gosh, can't see either of them. Here's the one, iron 0.77 for reduction, but it's undergoing oxidation, so it's a negative 0.77. And then chromium, I swear it was over here. There it is. Negative 0.50. So overall, we're going to have a negative 1.2, 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1.1 . 1 Oh, that's right, 1.27. Ugh, adding on the spot, sometimes a little stressful. So the voltage for the cell is a negative 1.27, which means non-spontaneous. All right, so that's the next step to us finally figuring out how batteries work. So do some problem sets with that, and then we'll come back. There's actually a second side to the organizer that we will look at in the next video.